Hello students, today I have the last 7 questions of this Neet 2018 paper series of code AA. So I am taking the question number from 39 to 45. Question number 39 to 45. And as I have told you earlier that the videos are long, about 1 hour. So you have to watch the full video only, then you can understand that how to apply the formula, the concept, and how to calculate, and so how to find the correct answer. So now the question number 39. The kinetic energy of a planet. The kinetic energies of a planet in an elliptical orbit. Elliptical orbit about the sun. About the sun at position A, B and C. At positions A, B and C are KA, KB and KC. Respectively. AC is major axis. AC is major axis. AC is major axis and SB is perpendicular to AC. And SB is perpendicular to AC. AC at the position of the sun. At the position of sun as shown in the figure. As shown in the figure. Then now the options. Now this is given here. This is the elliptical orbit. This is the sun. Here this point is A, this is B, this is C. Now you will find the relation. So it is asking then A, K, B greater than, no, less than. KB less than KA less than KC. And second, KA greater than KB greater than KC. Third option is KA less than KB and less than KC, less than KC. And now fourth option, KB greater than KA greater than KC. These are the options. We need to find the kinetic energy of solution. Kinetic energy. Energy of planet this is equal to half m v naught square. V naught, the orbital velocity. V naught orbital velocity. And mv naught square equal to, this is your 1 by 2 g m upon r. This is the kinetic energy, and r is what? The distance of the planet from the sun. R, distance of planet from sun. So now you can see that this distance is larger one. It means that kinetic energy at the point A, that will be the minimum one. And you can see at the point B and at the point C, the distances are not the same, they are different one. So here the velocity that we find, this is the velocity V naught. Similarly here the velocity, like this, V naught, V naught. So now velocity at these points A, B, C are not equal. The point which is far away from the sun is at a higher velocity, and the point near the sun, the velocity is less. So this is giving you the more better to write. So this one is this is equal to half m v naught equal to r omega. This is r omega whole square. So this is your 1 by 2 m r square omega square. V naught equal to r omega. Omega is the angular velocity. They are also having the angular velocity. So you can see that kinetic energy directly proportional to the distance. This r square. This kinetic energy is proportional to r square. So you can see that at the point A the velocity is maximum, and B this is now less, and at C this is now least, because this distance is more than this distance. So we are having the relation that this distance suppose r, this distance suppose r a, this is your suppose r b, and this is suppose r c. Then what we are having? r a greater than r b greater than r c. So now we are having what? That this kinetic energy Ka, so Ka greater than Kb greater than Kc. So the kinetic energy of these planets would be in the descending order. Kinetic energy at A is the highest, B is less, and at C it is least. So now we are having the relation second. So our option is second. So this is what to apply the concept. The kinetic energy half mv square, then v equal to r omega, because this is rotating about the sun, so it is having the angular velocity also. Now we are taking the question number 40. Question number 40. If the mass of sun is 10 times, if the mass of sun is 10 times smaller then, and the universal gravitational constant and the universal gravitational constant, universal gravitational constant were 10 times larger, were 10 times larger in magnitude. In magnitude, which of the following is correct? Which of the following is correct? Is not correct? Is not correct. First is time period of simple pendulum on the earth would decrease. Time period of simple pendulum on the earth would decrease. And second option, walking on the ground would become more difficult. Walking on the ground would become more difficult. And now third option, raindrops will fall faster. Raindrops will fall faster. And fourth, G on the earth. G on the earth will not change. Will not change. This is the option. You are giving that mass of the sun is 10 times smaller and that the universal gravitational constant is 10 times larger in magnitude. Which of the following is not correct? Let us find the gravitational pull between the sun and earth. Gravitational force between sun and earth. This is equal to F equal to G m upon R square. So what we are doing? Mass m, mass of sun, and m the mass of earth. So now F dash, when this F dash equal to G, you will take 10 times. This is giving 10 times larger, 10 times larger. G and the sun's mass is 10 times smaller. This is now m by 10 into m upon R square. So this 10 and 10 will cancel. So we are having this what? G m upon R square. So now what is happening? That the force will not change. The gravitational force between the sun and the moon, between the sun and earth will not change. So what is the factor that will change here? Let us take the gravitational acceleration on the earth. Gravitational G on earth is equal to G m upon R square. R e m e. This m is the mass of the earth, R is the radius of the earth. So there is no change in answer, but when this G is 10 times, we are asking that G is 10 times. So G dash is equal to 10 G into m e upon R e square. Now then what? This value G dash is equal to 10 G. It means that the gravitational acceleration will increase. It will be 10 times of the initial value. So what will happen? Now we see one by one. Time period of the simple pendulum on the earth would decrease. Now time period. T equal to 2 pi square root of L upon G dash. L upon G dash. G has increased, time period increased, this G dash is more, so temperature will be less. Temperature will be less. And working on the earth would be more difficult. This is right, because the value of G will be more, so it will be more difficult to move on the earth. And raindrops will fall faster because the value of G is more, so definitely the raindrops will fall faster. G on the earth will not change. This is now G dash on the earth. We find that this is now 10 times of G. So actually our solution is to what given here, that is the temperature of simple pendulum on the earth would decrease. Is incorrect. This is incorrect. Will what is given here? Upon R square 2 pi L upon G. So here the incorrect is the value of the first option, that the temperature of the simple pendulum will decrease. So our option is, answer is first. Because of this, there may be change in the effective length, or the time. It will be very difficult for the simple pendulum to vibrate. So because of that, the time period will increase instead of decrease. And now question number 41. Now 41 question is here. A solid sphere is in rolling motion. A solid sphere is in rolling motion. In rolling motion, a body possesses. In rolling motion, a body possesses translational kinetic energy, KT, as well as rotational kinetic energy. Rotational kinetic energy. Kinetic energy KR. Kr simultaneously. The ratio of Kt ratio Kt plus Kr for the sphere is first option is 10:7, second is 5:7, third is 7:10, and fourth is 2:5. This is the options. Now solution. Now this kinetic energy Kt equal to half mv square, and this Kt plus Kr, this is equal to half mv square into 1 plus k square upon r square. So now we take the ratio Kt ratio Kt plus Kr. So this is equal to half mv square upon half mv square into 1 plus k square upon r square. Half mv square we will cancel. So k square upon r square. This is equal to 1 upon 1 plus 2 by 5. For solid sphere, this is 2 by 5. So 2 and 2, 5 and 2, 7, 7 by 5. So this is now you have 5 upon 7. It means that the correct option will be second. So here we have the answer. This is now second one. Now ratio will be 5:7. 5:7. So you have to remember that the translational kinetic energy is half mv square, and sum of the translational and rotational kinetic energy, this is equal to half mv square into 1 plus k square upon r square. So that you find the ratio and then put the value of k square upon r square. So that will give you the correct answer to this question. Now question number 42nd. A small sphere of radius r. A small sphere of radius r falls from rest in a viscous medium. Falls from rest in a viscous medium. As a result, heat is produced. As a result, heat is produced due to viscous force. The rate of production of heat. The rate of production of heat, rate of production of heat when sphere attains its terminal velocity. When sphere attains its terminal velocity is proportional to now options. First, r raised to power 5. Second, r square. Third, r cube. Fourth, r4. Now the solution to this question. Rate of heat produced. This we have to find. So power. This is equal to what? W upon T. This is what? This is joule. This is upon second, joule per second. So this is the rate of heat produced. Rate of heat produced. This is equal to so much. So what we have? Rate of heat produced that we can get from here. P equal to, this is equal to your F into X upon T. So this from here P equal to F into V. Now we apply this formula in this. So the power that we always give it the definition, the rate of doing work. The rate of doing work means here the heat is being produced, so this is the rate of heat produced. So this power it gives you the rate of heat produced. So now this F, viscous force. F equal to 6 pi eta r V. This is the formula given by the Stoke, and V the terminal velocity. Terminal velocity V equal to 2y9 r square upon eta into rho minus sigma into g. This is the velocity. So what do you have? You put these values here. Therefore, P equal to 6 pi eta r V into V. V into V. This is now your V square. So this is 6 pi eta r and this is now V square. So just to square to this one, it means that we have to square this one. So this is equal to 6 pi eta r. Now square to this one, so this is now your 4 by 81. And this is r to the power 4 upon eta square into rho minus sigma whole square into g square. What we have is eta will cancel, and this will cancel 3 by 2 times 3 into this is now 27. So how much heat is given to here? So we are getting that this P is equal to, this is now you 4 to the 8 by 27, and this is now your pi will remain as such, and 1 eta this is now so much, and this R. Now this R into R to the power 4. So this is R to the power 5. R to the power 5 upon eta into rho minus sigma whole square into G square. Now dependence of this P on radius is R to the power 5. So all are the constants. P equal to K R to the power 5, where K is equal to 8 by 27 pi upon eta into rho minus sigma whole square into G square. So what we have, that this P is proportional to R to the power 5. It means that our right option is first. That the rate of heat produced is proportional to the fifth power of the radius of the sphere. So our answer is first, R to the power 5. So this is how to apply the equation formula for the viscous force given by Stokes. V the terminal velocity. Terminal velocity is given by this one, and more you may have. Only thing you have to understand here, that this power represents the rate of heat produced, because this is now joule per second. Joule per second. The heat is also measured in joule. So this will give you the rate of heat produced. And now question number 43. Power radiated by a black body. The power radiated by a black body is P, and it radiates maximum energy at wavelength lambda naught. If the temperature of black body is now changed, if the temperature of black body is now changed, so that it radiates, maximum energy at wavelength at wavelength 3 lambda naught upon 4. The power radiated by it, the power radiated by it becomes Np. The value of N is now the options. First option is 256 upon 81. Second 4 by 3, third 3 by 4, fourth 81 upon 256. This is the question. So we will use the Stephen's law. According to Stephen's law, E is proportional to T to the power 4. E is the amount of radiant energy emitted by the body per second per unit area. Per second per unit area, it means that this is the power P. So it will be defined that the rate of doing work. So this is the energy per second. If we the area we take on this side, then this is E upon T. E upon T, this is our power. This is given here the power radiated. So E equal to sigma T to the power 4 A into T. A the area, T the time. So E upon T. This is equal to your sigma T to the power 4 into A. So this is now power P equal to sigma A 2 to the power 4. So what we are getting? That this T is proportional to P is proportional to T to the power 4. So E upon T. This is now power P equal to E upon T. E, this is the power radiated by the body. So now we are having this here, that first it is given at wavelength T naught. This is lambda naught, and then it is said that wavelength becomes 3 lambda naught upon 4. So now we will have base displacement law. Lambda into T equal to constant. So first this is now lambda naught into T equal to, then this is your 3 lambda naught upon 4 into T dash. The temperature is changed. So from this lambda dash, lambda naught will cancel, and we will get T dash equal to 4 upon 3 into T. So now you apply the formula. P dash upon P. This is equal to T to the power T dash upon T. This is raised to power 4. From here that we get. So this is equal to P dash. P dash is equal to N into P. This is upon P. And T dash is your 4 by 3. T upon T raised to power 4. T and T will cancel. And P and P will cancel. So N equal to. This is now your 4 times. So 16 to 256. 4 times. So this is now 81. So now value of this N, this is equal to 256 upon 81. So now right answer is first. Our answer is first. So what we have to use here, since this is given the maximum energy radiated by the body at the wavelength lambda naught, and then at the wavelength 3 lambda naught upon 4, wavelength has decreased. It means that temperature will increase according to Wien's displacement law. So we will use this one, then T dash equal to so much, so P dash upon P, then you find and calculate the value of P. So this is how to use the equation, the formula given by Stephen, by the Stephen, and then using the formula of Wien's displacement law. Now question number 44. Now in 44, two wires are made of same material. Two wires are made of same material and have same volume and have same volume. The first wire has cross-sectional area A. The first wire has cross-sectional area A, and second wire has cross-sectional area 3A, and second wire has cross-sectional area 3A. If the length of the first wire, if the length of first wire is increased by delta L, is increased by delta L. On applying a force F, on applying a force F. Now, how much force is needed how much force is needed to stretch the second wire, to stretch the second wire, to stretch the second wire by same amount. Second wire by same amount. By same amount. Now first option is, this is now your 4F. Second is 6F. And third is 9F. And fourth is the F. So now here this is given that the made of same material having the same volume. Same volume. Volume is the same. Cross-sectional area of the first wire is your A and second is of this now 3A. So now we take the first, the length will be how much? Volume of first wire equal to volume of second wire. Volume of first wire, this is now A into L. Second wire, this is now 3A into L dash. Suppose this is now L dash. Then from here we get this L dash equal to L upon 3. Okay, this is the relation. The lengths of the wires, because the lengths are not equal and area of cross-section are also not equal, but volumes are equal. So it means that they have a relationship between the lengths of the two wires. Now it is asked that if the length of the first wire is increased by delta L on the applying of the force F, then how much force is needed to state the second wire by the same amount? Same amount means that its length must also be the delta L. So we know that the Young's modulus Y equal to F upon A into delta L upon L. This is the formula. So we have to find this delta L. Delta L. So this delta L equal to this F upon A F upon A into L upon Y. This is so much. So for first wire of cross-sectional area A, for first wire delta L equal to F upon A into Y upon L. This is given the L. For second wire delta L dash equal to F upon, now area of cross-section is 3A. For second, this is given 3A into L, this is now your L dash upon Y. L dash is here, L upon 3. So this becomes your delta L dash equal to F upon 3A into L dash equal to L upon 3 into Y. Now what is according to question? According to question, delta L dash equal to delta L. This is given to us. So delta L dash, this is equal to F upon, this is now suppose force is F dash. So F dash upon 3A into L upon 3Y equal to F upon A into L upon Y. So this Y will cancel and this A and A will cancel, L to L will cancel. So what we have? F dash equal to 9F. F dash equal to 9F. So 9F, then our option is what? Third. our option answer will be third one. So this is now direct application of the Young's modulus, but we have to understand the question. First, that the volumes are equal. To make the volume of both the wires are equal, then this will find the length, because area approximation are given here, but length is not given. So by this condition, you have to find the length of the wires, and then find the delta L and delta LS, and put the value and equalize them. That will give you the force F dash equal to 9F. So our correct answer is your 9F, the third option. Now the last question, 45. The last question is given here. A sample of 0.1 gram of water at 100 degrees Celsius and normal pressure and normal pressure 1.013 into 10 raised to the power 5 Newton per meter square, requires 54 calories. Requires 54 calories of heat energy to convert to steam, steam is 167.1 cc. Converts to steam is 67 so much. The change in internal energy, the change in internal energy of the sample is, now your options are 42.4 joule, second 208.7 joule, third 104.3 joule, and now fourth 84.5 joule. This is the question. Now the solution. You see that the amount of the water is given at 100 degrees Celsius at normal pressure, and so much, requires 54 calorie of heat energy to convert to the steam is 167.1 cc. It means this is the volume of the steam. The change in internal energy of the sample is 42. Then they give the options. So here we apply the first law of thermodynamics. First law of thermodynamics. Delta Q equal to du plus pdv. Du you have to find. Du internal energy. This is now your delta Q minus P dV. dV the change in volume. So now 1 gram of water. We have to find this one. Here delta Q is equal to, this is given to 54 calorie. 54 calorie. And we know the relation that this 1 calorie equal to 4.18 joule, because the answers are given in the joule. All options are in joule. So we have to take convert this into the joule. And this is your delta Q equal to 54 into 4.18. And this value will come out to be 225.72. So much joules. Then P delta V. So V1, the initial volume. Volume of water. This is your mass is given here. Volume equal to mass upon density. So mass is 0.1 into 10 raised to the power minus 3 and density is 10 raised to the power 3. So this is 0.1 into 10 raised to the power minus 6. So much meter cube. You have to take in meter cube. This is given in cc. And V2, this is 167.1 cc. So this is 167.1 into 10 raised to the power minus 6 meter cube. So much. So delta V equal to 167.1 into 10 raised to the power minus 6 minus 0.1 into 10 raised to the power minus 6. So this is 167 into 10 raised to the power minus 6. So much meter cube. So now put all the values in this equation. Now P is given to be so much. This is now value of P. So what we have? Therefore, delta du equal to delta Q minus pdv. So du equal to, this is now your 225.72 minus P is 1.013 into 10 raised to the power 5, and this delta V is so much, 167 into 10 raised to the power minus 6. So now this powers will cancel, will be here 1, and then you apply. So this is now your 225.72 minus this will come 16.9. that you subtract and you will get it 208.82. So much Joule. So we are very close to this option, 208.7. So this is what our right answer to this question is. Your second answer is second. So this is, you have to apply the first law of thermodynamics. Delta Q is given, that so much heat is supplied, and then P delta V, P is given, delta V you find, that so much is the initial volume, volume equal to this mass upon density. So mass is 0.1 gram, you convert it in kilogram, this is in meter cube, so much meter cube, and then you find this V2 is given here, this is in cc, cubic centimeter, convert it in meter, 10 to the power minus 6, then to find to this one, and then calculate and find the right answer. So this is the question number 45, and this is the complete paper of Neet 2018 series AA. I have told you earlier that in the same year, suppose this 2018 or 2019 or 2022 or 2021, whatever the series are there, they all have the same questions, but sequence are different, and the answers which are options are given, they are also changed, so that there could be no copy or no cheating of the between the students, among the students, so that they could have their own answer. So this is how to solve this question paper of Neet 2018. This is now complete one, and then on the next I may take either a sample paper of 2021 or the 2017, whatever is possible that I get. So this is what the Neet 2018. You all like, share and subscribe the video. Thank you very much.